Thanks. It's Shoup. That's cool. I always forget to do that. Yeah, so I'm Randy Shoup. Everything else was true. So I want to talk about scaling your architecture with services and events. Last time I was here, I talked about services. Some of the things that we talked about last year, I'm going to compress a little bit. But basically, this is the answer to all the questions that people had. That's the whole next set of the talk. It actually was first a day-long workshop that I did in Israel a couple of months ago. So this is going to be one of those things where it's going to be a little bit fast-paced, and I know you guys can handle it. All right. We're talking about scaling. What we are not talking about, none of the techniques I'm going to talk about here are great for your 5-person startup, but they are good when you are 50 people, 500 people, 5,000 people. So I do want you to keep in mind that just because it's a cool thing that Google does is not the reason that you should do, you shouldn't do the same thing in your garage. Cool. Let's talk a little bit about how these big companies you've heard of have evolved to microservices. So eBay, depending on how you count, is on its 5th complete rewrite of its infrastructure. It started famously in 1995 as a toy project by the founder over a 3-day weekend. He was playing around with this new thing called the web. He was working at Adobe at the time. I always want to say he was typing away on his laptop, but I guarantee it wasn't a laptop in 1995. It was probably some 486 monster tower with 1 mega memory or whatever. Anyway, so Pierre Omidyar wrote the first version of eBay. It was in Perl. Every item was a file. It was not intended to scale, and it didn't. The next iteration was a rewrite in C++. At its worst, it grew to 3.4 million lines of code in a single DLL. So if you guys think you have a monolith, we can talk. The next iteration was a rewrite in Java. I wouldn't call that microservices, but I would call it mini applications. So there were individual applications for, the selling part of the site, the search part of the site, the buying part, et cetera, times about 220 different applications that together laddered up to eBay. And then now it's fair to characterize eBay as a polyglot set of microservices. Twitter has gone through a similar evolution. It started famously as the world's largest Ruby on Rails application, which, by the way, it still might be. I love the code name that they used, which was the monorail. The monorail. The next iteration was a rewrite of the front end, mostly in JavaScript, a rewrite of the back end in services, mostly written in Scala, and now you can call Twitter a polyglot set of microservices. Amazon has gone through a similar evolution. So it started as with the front end in Perl and Mason, the back end in a C++ monolith, and you can actually still see evidence of that monolith in some of the old Amazon URLs. So if you ever see Obidos, O-B-I-D-O-S, in a URL from Amazon, that was the code name of the original monolithic application there at Amazon. And you might ask yourself, why would that still be in the URLs? It's because search engine optimization. Cool. The next iteration was a rewrite in services, a lot of Java, a lot of Scala, lots of different languages. It basically took Amazon from the years 2000 to 2005 to rewrite their entire infrastructure in services. What happened in 2006? AWS. And then they started taking over the rest of the world. I used to be a retailer. If you're a retailer on the planet and you think Amazon's not your competitor, you're not paying attention. All right, and now you can characterize Amazon as a polyglot set of microservices. So does this look like a pattern? It's okay to say yes. Awesome, great. You could say C, you could say yeah, whatever you like. There are 2 parts to this pattern. Nobody started with microservices, but past a certain scale, which legitimately not every company is going to reach, but past a certain scale, everybody co-evolved to something that we now call microservices. Does it make sense? Cool, all right. Because I want to keep hammering home this point, I want to use a quote from my wonderful friend Martin Fowler, who wrote the refactoring book. He's wonderfully brilliant and also sarcastic. I love his first law of distributed object design is don't distribute your objects. If you do not need to build a distributed system, please don't. Now that I've said that, I'm going to tell you how to build a distributed system. Okay, microservices and events. First, I want to talk about how to migrate from your monolith into microservices, assuming you're at the right stage of your development where that makes sense. And then I want to talk about the challenges of data in microservices. So how do we do shared data? How do we do joins? How do we do transactions? And then finally, I want to talk about some challenges of using events at large scale, including event duplication and event ordering. Okay, here we go. Migrating to microservices. So I should probably still maybe define what I mean by microservices. There have been a lot of blog posts around over the last several years like, oh, a microservice is like less than 200 lines of code, or a developer should be able to rewrite it in 2 hours, and I don't believe any of that stuff. The micro in microservice is the scope of the interface. The scope of the interface, yeah? If the interface is simple and single purpose and well-defined, that's a microservice. It doesn't matter to me how complex the implementation is, right? The interface to a payment service is super simple. I would like to pay Ollie this, 100 euros with this particular credit card. That is as trivial an interface as you're going to get, but anybody who has done payment systems knows that's a super complex implementation. Does that make sense? Cool. All right. Single purpose, simple, well-defined interface, modular and independent. So that payment service that I built to pay personally to Ollie, maybe I could also use it to pay my vendors or my suppliers or my customers or something like that. And the critical thing that we know now that we, by which I mean the I part of we, did not know in the 90s is that we really need to have isolated persistence. Yeah? If I'm going to call something a service, it really needs to own its own database. Why, you might ask? If somebody is able to read and write my data from behind my back, what guarantees can I make about invariance in my system? None. Absolutely none. That's right. I can make 0 guarantees. If somebody can read and write data behind my back, I can make absolutely 0 guarantees that my business logic gets executed, 0 guarantees about any invariance. All right, cool. Now I want to talk about extracting microservices from a monolithic database, and then we'll talk about the problems that we have now introduced and try to solve those problems. Okay, so this is an example, a simplified example of Stitch Fix, where I used to work before I just recently went to WeWork. So we actually have 70 or 80 different applications and services, but one monster shared database in the center. So what we want to do is we want to decouple those applications and services from that shared database because it is a single point of failure, it's a single performance bottleneck, and it's actually, even more importantly, a single kind of functional bottleneck for the team because the team is having to step on each other's toes and coordinate with each other to get any work done. So I'm going to show you this in an even more simplified form. So let's pretend that there are 3 tables instead of 175, and let's pretend that there are 2 applications instead of 80. Okay, so the first step we're going to do is we're going to define a service. Let's imagine we're trying to define a service around clients or customers or something like that. So the first thing we're going to do is we're going to create a service with one of those simple, well-defined interfaces. The next thing we're going to do, and by the way, those lines that I just moved, that's the hardest part. What we want to do next is we want to have all the applications, all the places in our system that were directly using the table, now we want to have them use the service. I want to be super clear that moving lines on an architecture diagram in 1 second, that just represented several person months of effort. It might represent several person years of effort. But I guarantee you cannot move forward unless you have finished this step. Because the next step is to pull that client table out into its own database and associate that with the service. Does that make sense, at least conceptually? Yeah, the details are super complicated, don't hear otherwise, but these are I've never seen this kind of process done without following those steps, and you kind of have to follow them in that order. Okay, so now we've done that with the client service, we'll do the same thing with items, and we'll do the same thing with SKUs or styles. That's basically at Stitch Fix, that's the metadata about the clothing inventory that we have. And to hammer home the point about isolated persistence, these are the boundaries. These are the boundaries. Does it make sense why I'm hammering that point home? Yeah, the boundary is not just the business logic of the service, it's also the data of the service. All right, cool. So now that we've gotten in this place, like we're all done, all our problems are solved, life is wonderful, right? I so wish that were true. But in fact, we've now introduced a bunch of problems, which now I'm going to help us solve. So there are some challenges around, once we had a monolithic database, we had some wonderful situations, wonderful properties of that, and we still want to retain some of those properties as we broke them up into microservices. So how I want to approach this part of the talk is I want to give you a couple of architectural tools in your toolbox that maybe you already have, I hope, and then I want to use those tools to talk about shared data and joins and transactions. Okay, so the first is these 2 architectural tools. The first of the tools is the idea of a system of record. Who's heard this term, a system of record? Yeah, surprisingly few. Okay, the idea here is that every piece of data in your system that matters is owned owned by one and only one part of your system. So there is one and only one place that is the owner of customer data. There is one and only one place that is the owner of item data. There is one and only one place that is the owner of, I don't know, payment, something like that. But there are a ton of other parts in our system that care about customer, right? Like almost every other part of our system cares about customer because we actually are trying to serve our customers, right? Okay, cool. Every other place that is not the system of record, but every other place in our system is a read-only, non-authoritative cache. Every one of those words is super important. Read-only, so if I ask the customer search service or the billing service, hey, what's the customer address? It might be able to tell me, but I can't update the customer address from there. Yeah? That's the read-only part. The non-authoritative part, I could ask the billing service, hey, what's the current customer address? It might be stale. I mean, it might be stale by a second or a microsecond or a day, but it's not the authoritative source of that information. Does it make sense? And then cache, it's a cache, which means it has all the fun properties of caches. Remember the two problems of computer science, naming things and cache coherence, and off by one errors? Come on, guys. Naming things, cache coherence, off by one errors. The two problems of computer science. Okay, great. We'll explain it more later if it needs to be explained. Okay, every other part is a read-only, non-authoritative cache. Who's heard of DNS? Yeah, this is how DNS works. Okay, the next architectural tool is events. So Wikipedia defines an event as a significant change in state. I like to say it's the statement that something significant occurred. So we are mostly familiar with building three-tier systems. There's maybe a presentation tier, an application tier, and a persistence tier. I think we are missing something if we don't add a fourth fundamental architectural building block, which expresses a state change, and I'm going to call that an event. Cool. So now that we have microservices and we have events, how do we express events in our microservice system? Well, a key idea that I like to put into practice in places that I work is to consider events as a first-class part of my service interface. So the obvious part of the interface of my service is the synchronous request-response part, right? So it could be REST and JSON, it could be gRPC and protobufs, God help you, it could be Corba, it could be DCOM, whatever your front-end sort of synchronous request response, that's obviously part of your interface, right? But the other maybe non-obvious parts of your interface is all the events that your service produces, all the events your service consumes, and we're not going to talk about this much today, but any bulk reads and writes, writes out to an analytics system, reads in from some other third-party system, something like that. All those things are part of your interface. So what I want to underline is that your interface is any mechanism that gets data into or out of the service. Does it make sense? Cool. All right. Next, so now I want to use those tools to figure out how we can get a bunch of those wonderful things we used to have in our monolithic database. So first I want to talk about shared data. So let's motivate the problem. In a monolithic database, it's really easy for me to leverage shared data. I just have some, metadata table or some common table, and I point at it with my SQL, and it's very easy. But where does that shared data go in the microservices world? I will give you three options. The first option is simply look it up in real time. Yeah? This is totally legitimate, by the way. So in this particular example, a fulfillment service that's going to ship physical boxes through the physical mail needs to know the customer's shipping address. Like, that's a thing that the fulfillment service needs to know. It could completely legitimately just simply call the customer service and say, hey, what's the customer's shipping address? There is absolutely nothing wrong with this technique. Sometimes, though, it doesn't meet your operational requirements, because maybe I want to fulfill packages if the customer service is down. Maybe this would put too much load on the customer service. Maybe the customer service is too slow. There could be all these operational reasons why this isn't a technique that works, but if you don't have those operational reasons, this is a totally legitimate technique. The next technique is to use events. So we will still keep the customer service as the system of record for customer. So if we ever want to update the customer's address, we do it through the customer service. But then whenever that address is updated, the customer service produces an event, which then the fulfillment service listens to, and the fulfillment service locally caches the customer's shipping address. Does it make sense? Cool. Yeah, and so notice that it's a read-only, non-authoritative cache, like it's on the other side of this event bus. Great. If this looks unfamiliar, I will tell you in a few moments why that's very common. Option 3, though, is if the shared data that you have is kind of slow changing metadata, it's perfectly legitimate to ship it as code. I don't think this is a good solution for customer data, but something like at Stitch Fix, for example, we had metadata around the different colors that, that clothing could be, or the different materials, or something like the US states, right? The US has 50 states. That has not changed in the last 60 years. Maybe someday, you know, Puerto Rico will become a state or something like that. That would be nice, and maybe we could treat them well. But someday there will be like 51 and 52 states. We're going to have a lot of lead time to know that. Does it make sense? So I do not need to be microsecond accurate with this thing. Does it make sense? Cool. EU membership might be the same thing, but I'm not going to go there. All right, cool. Great. So that was shared data. Now I want to talk about joins. So let's motivate the problem. If I have everything in one database, it's really easy for me to join. Take a look at the select. I just took select from A, and I said select from A, inner join B on join condition. Super simple, super easy. Where does this stuff go in a microservices world? Okay, 2 options. Again, we could just simply join in the place that we need it, right? So the client service or the client application, like whatever service it needs this join, could simply read from the one side and read from the other side. Does it make sense? So in this particular example, I want to show an order history page to my customer. We go and read from the customer service on the one side, get her information, then we go and get all of her orders on the other side. Super simple, right? This is every web page on the planet. This is every web page on the planet, yeah? Okay, cool. And again, so totally legitimate. This is a completely legitimate technique. Another technique, if that doesn't meet our operational requirements, like maybe I want to be able to show that order history page with the order services down or the customer services down or something like that, or maybe it's too slow to compute that join in real time, I have this option, again, which we will use events for. So in this particular example, let's imagine that we want to have an item feedback service. So Stitch Fix ships out boxes of items to customers. They keep some things, they return other things, and they give us feedback about all of them. And so we want to associate the feedback about a particular shirt, let's say, and we want to aggregate it all together, right? So we've sent this shirt, or instances of this shirt, out many, many times, and we've gotten feedback about it, and we want to put that together. And also, we have many shirts. Okay, so the item service is going to produce events. The order feedback service will produce events, and then our item feedback service will listen to both of those events and kind of materialize that view, maintain that join locally. Does this make sense? Yeah. If this seems unfamiliar, I want to disabuse you of that notion. You actually use many systems every day that are like this. For example, if you use a database system that has materialized views, yeah, fewer and fewer every year, because basically it's only the enterprise class databases. And when I say enterprise class, I mean you pay for them. Those are the ones that have this feature. Fine. Most NoSQL systems, so if you use Cassandra or React or Voldemort, you're already doing this up front before you write to the NoSQL system. Search engines. Who uses a search engine in your system? Yeah. Almost all search engines that you would use are joins of different entities from different parts of your system. Who has an analytics system in their plate? I hope every hand is going up, by the way. You're just being, I hope, shy. Yeah, if you have an analytics system at your company, that is also, almost by definition, a join of lots of different entities across your thing, right? Cool. So you use this technique all the time, even if you're not aware of it. All right, cool. That was joins. Now I want to talk about transactions. Let's motivate the problem. Again, in a monolithic database, we have a transactional boundary within the database, so I can, if I want to update A and B together, or insert into A, update into B, do that atomically and with ACID properties, I can do this. I can begin a transaction. I can say insert into A, update B, commit or rollback, all good, right? This is super familiar, right? But when we've split the data across services, each of which has its own database, how do we do this? We don't. I'm going to tell you what you can get instead, but we don't do that. So at this point, I like to quote Pat Helland, who's a wonderful, brilliant writer, and actually the guy who built transactional two-phase commit into first Tandem and then Microsoft SQL Server, so he kind of knows a little bit about distributed transactions. He says, even he says, In general, application developers simply do not implement large scalable applications assuming distributed transactions. There's a wonderful paper referenced here which is called Life After Distributed Transactions, an Apostate's Opinion. An apostate is like a heretic. You remember yesterday's Simon's talk, heretic? Like that's somebody who violates the religion. So apostate is just a fancier word for that. Yeah, so he was part of the distributed transaction religion, then wasn't, and now wrote the paper about that. Great, fantastic paper. It's really readable and really funny too. He also has a simpler way to say this, which is grown-ups don't use distributed transactions. Look, they work from an academic perspective. It's not like a distributed transaction doesn't function. It just doesn't work at scale. Why? Because for all the resources that are involved in the transaction, they all have to be up, they all have to be fast, and so it ends up being a performance bottleneck and a scalability bottleneck. Who uses the cloud? Keep your hand up if your cloud vendor implements distributed transactions that you can see. Right, wrong. No cloud vendor, good job. Nice try though. One hand was remaining. No cloud vendor on the planet exposes distributed transactions because they don't do them typically. Okay, cool. What can you have instead? You can have this thing that we'll call a saga, which is a fancy term, or maybe something that's more actionable or more evocative is a workflow. So let's model that transaction as a workflow of individual atomic steps. What do I mean? So let's imagine that I want to do these updates, do writes to A and B and C, and I'd like them to be atomic, consistent, isolated, and durable. Well, I can't have atomic, I can't have consistent, I can't have isolated, but I can probably give you durable. But I'll tell you what you can have. All right, so we're going to re-implement it as a workflow. So first we're going to make some updates into A. That will produce one or several events. B will then do its work and produce one or several events, and then C will do its work. You are correctly asking in your head, what if something goes wrong? That's an excellent question. I'm so glad you asked. So what you do is you roll back by doing compensating operations in the other direction. Does it make sense? So if you notice that there's a failure at the C point produces some flavor of like undo events or customer no longer associated with the company or whatever, like produces some events that let people know that we're needing to unroll the transaction, and then that propagates to B, which then propagates to A. Does it at least conceptually make sense? Yeah, cool. Because, not just because, but in particular because Simon told us that serverless is the future, and I actually strongly was really inspired by his talk yesterday, I want to tell you how you can use serverless in this area. So particularly the flavor of serverless that is the classic functions as a service. What we're talking about in A, B, and C here is really simple event-driven processing. The processing is stateless, and it's triggered by an event. So this is a great place to use something like Amazon Lambda or Google Cloud Functions or Azure Functions. Does that make sense? It's by no means the only way to implement it, but if you're trying to figure out what in the world could I use serverless for, this is a thing that you could use serverless for. Does it make sense? Cool. All right. If that workflow saga thing felt very uncomfortable to you, and it felt like there's no way that systems could possibly work like that, I want to show you that there actually are. So, payment processing. The payment that I would have liked to have made to Ollie, that is a workflow, yeah? Who thinks that anywhere on the planet that I could have paid Oliver with my credit card and that happens atomically, consistently, isolatedly, and durably? Yeah, let the record show that no hands went up. That's true. Excellent. Yeah, so there is no payment system on the planet that works immediately in that way because banks don't do distributed transactions with each other. Similarly, expense approval. Who will have to submit expenses when they go back to their companies? Yeah, who gets their money atomically as soon as they hit submit? Yeah, nobody, right? Instead, what happens is it goes to your boss, and she approves it, and then it goes to her boss, and she approves it, et cetera. Does it make sense? And then they'll start the payment processing workflow, and you might get your money several days after that. Cool. Travel. So I love Budapest. I love to visit. I don't live here. I do live in San Francisco, and I came via Mallorca. So I was in Mallorca for another conference where I gave this talk, and then, so if you asked, where was Randy, during last weekend, the answer would be Mallorca. And then, now, if you ask, where's Randy, the answer is Budapest. But there was a transition period where Randy was in the air between Majorca and then Düsseldorf, and then there was another transition period where Randy was in the air between Düsseldorf and Budapest. So if you ask, where is Randy in those areas, the answer is in process. Does it make sense? The answer is somewhere in between La Palma and Düsseldorf, or somewhere between Düsseldorf and Budapest. Does it make sense? Is that hard to reason about? No, that's super easy to read. This is the world. The world is, where's Randy? Oh, he's in transit, right? He's somewhere between point A and point B, and that is not bad. So if you decide to do these ideas I'm suggesting, and you take what you thought you needed to have in a distributed transaction, and you spread it over a workflow, and if you're worried about the idea that, hey, what if somebody asked me the state, you can say it's in process. Does it make sense? You can say the payment is processing, the approval is pending, right? Randy is in transit between city A and city B. So these are very natural things that are part of the physical world, and we just need to model that idea as a first-class part of that interface. Does it make sense what I'm saying? Cool, all right. The other example is everything that you guys do every day, I hope. So who writes code for a living? Wow, I so love so many hands going up. That's great. Keep your hand up, please. Sorry. Keep your hand up if, when you hit return in your IDE, it is immediately and atomically deployed to production. Let the record show that no hands stayed up. Good for you. There's somebody in the back, but it's not atomic, dude. Yeah, unless you're editing production. Oh God, please don't do that. Actually, no. We'll talk later. Yeah, right. No, but does that make sense? What you do on your IDE is you type away, you know, or hopefully with Mel's thing, you're going to draw boxes and lines, and you won't even doing it. It'll be the business people. Like, that's super awesome. But somebody is doing some flavor of programming or telling the system what to do, and then at some point we say we like that idea, and then we run a bunch of tests. You guys are running tests, right? We run a bunch of tests, then we deploy it to production, and go. So I'm a huge, huge fan of continuous delivery, don't get me wrong, but there is no such thing as atomic delivery. Again, if we ask, what is the state of the system? Oh, well, there's version 11 on Randy's laptop, and then there's version 10 in production. Is that weird? No, that's super normal. Does it make sense? Cool, all right, great. Who has heard of, one more thing, because I just can't help myself. Who's heard of database isolation levels? Wow, this is an awesome crowd. I love you guys. Keep your hand up if you run at serialized. All right, very few. Serialized is the real distributed transaction. For those of you who, if you don't know this, don't worry about it. You can look it up if you're interested. But usually, at scale, people are running a lesser isolation level. They're running read committed or even read uncommitted, God help you, where you can see dirty reads, dirty writes. So my point is, even those of you who think you are running in a strongly consistent system probably aren't, except for the one guy who had his hand raised. Does it make sense? Cool, all right. There are two ways to do these kind of sagas. These are fancy terms, and because I love fancy terms, I'm going to use them, but then I'm also going to explain them in real language. So the first way to think about sagas is something called choreography. So choreography is just a fancy way of saying dancing. It's dancing. There is no central coordinator when you're dancing. Yeah? You might have a pattern that you follow, but there's no central coordinator among all the dancers, particularly in a ballet or something like that. Okay, so you can definitely do these kinds of sagas without a central coordinator. So in that case, there would be no central management of the workflow state, but state transitions entirely happen, you know, as we go along. So the state transitions are just happening through events, and there are only implicit guarantees that the state machine is going to terminate in one end or another end. Is that making conceptual sense? Like, it might terminate in this end, you know, hopefully, we hope, and then it might also terminate in this other end. But the guarantees are implicit. There's no coordinator in the system that's making that happen. Does this seem kind of uncomfortable? It doesn't? Seems a little uncomfortable, right? But, because you know where I'm going to go next. This is how the economy works. This is how the economy works, right? There is no central coordination of, anymore. There is no central coordination of this shop produces this thing, this other shop produces this other thing, they talk to each other. Like, there are individual event relationships, Yeah? There are individual transactional relationships, but there is no central coordinator of this shop is going to produce X and Randy is going to buy it, et cetera, et cetera. Does it make sense? So like everything that we do day to day is in this uncoordinated, weird, choreographed state. So it's actually not that bad, because if I did a payment processing workflow and I didn't get paid, I would be annoyed and I would go back and I would say, hey, let's figure it out. Does it make sense? Like we would actually, as a human, we would just run the workflow again, or we would call somebody or something like that. We would resolve inconsistencies because that's what we do in the real world. Okay, so this is a totally legitimate technique, particularly for simple workflows. There are other techniques where we use a coordinator. So you could also imagine having a workflow coordinator, which could then, of course, maintain the state of the workflow. That could be the place where you ask, where's Randy? And the answer is in transit. That coordinator might guarantee termination. So I'll use the payment example because we usually care about payments. So the payment service might initiate a workflow with some bank A, which is going to send an event or some message to bank B. The payment service might also kind of orchestrate that as well. There might be other events. The payment service might talk to Bank C, or I don't even know finance very well, you know, the closing people or the reconciliation people or something like that. And then if problems happen, you know, we can roll it all back and then we can undo all the stuff. But the idea here is that the coordinator is now making sure, at least at minimum, the coordinator is guaranteeing that we reach a terminal state in our state machine, either that it's all the way done or that it's all the way rolled back. And typically the coordinator is maintaining the state and triggering the state transitions, and then optionally we can use events to connect things as well. Does this make sense? Yeah. I want to be super clear that it's not like this is better than the other. These are all trade-offs which you can make. Okay, cool. All right, wow. That was the challenges of data. Feel pretty good about that. Now let's talk about some challenges that we have introduced by putting events in our system. So the first one I want to talk about is event duplication, and the next one I want to talk about is event ordering. So event duplication. So let's motivate the problem. The problem is that in large-scale event-driven systems, the same event is going to be delivered more than one time. That is just a guarantee to happen. Why, you ask? Because networks. Because networks fail, so we might have tried to deliver it, and then we had to deliver it again. We might have to redeliver for other reasons, like maybe we had a failure, like an actual application failure on one end, and we have to redeliver the event. But for sure, the events are going to be delivered more than once. People are probably familiar with the idea that in event-driven systems, you have a choice of either doing at least once delivery, where you try to deliver, and if you fail, you give up, or at most once delivery, where you try to deliver it and you give up if you fail, or at least once delivery, where you try to deliver it and you keep re-delivering it until it succeeds. Does that make sense? At most once, at least once. If you're doing any events about things you care about, you're always in that at least once regime. Does it make sense? If you actually care about the event, you have to do the at least once strategy, which means you're going to have to be in this situation. There are very few examples in the real world of at most once systems. The obvious example are like logging, right? So if you're doing logs, if you fail to write the log, do you just collapse? No, you keep processing, right? Because the log's not the important thing, it's the business logic that you're executing that's more important. So if you fail to write a log, you don't give up on the business operation that you're doing, you complete that. That's an obvious example. The only thing that I can think of in reality is if you're doing high-frequency trading and you miss a tick, those ticks are coming like seriously millions of times a second, and so if you drop a tick, you don't collapse, you just keep on going. Does it make sense? Cool, all right. Okay, that's the problem. And just to motivate it a little bit more, if the transport ends up delivering the same event twice, event 2 comes twice, this consumer has to at least logically process that event only one time, logically. Okay, cool. There are several techniques, as with all these things. The first technique is if you happen to use an event delivery mechanism that guarantees you, for some value of guarantee, we'll talk about that later, guarantees you exactly once delivery. Some event systems are making this claim. So how is this actually working? It's not magic. The message bus is just simply buffering the messages and noticing what it's already sent, and if it's already delivered, event 2, it doesn't deliver it again. Does that make sense? That's how, there's no secret magic. It's just simply, which things did I deliver? Oh, I already delivered event 2 to Randy. I don't have to deliver it again. Cool. So this is a totally legitimate technique. Great. One of the other techniques is, I'll use another fancy term, is called idempotent processing. Idempotency people have probably heard that term, certainly in this audience. It's the mathematical idea that if I do f of x, if I do one function, that f of x is equivalent to f of x. So if I apply the same function multiple times, I get the same result as if I applied it only one time. So there are several kind of micro options within this broad technique. The first is something that's called an idempotency key. So the sender is tagging each event with some unique identifier. So in here it's like AAA, BBB. And then that gets propagated through. And so the transport it propagates those idempotency keys as part of the message. And then the consumer is just simply remembering, oh, it's already seen AAA and BBB, so it doesn't reprocess the message. Does it make sense? For those who are paying close attention, is this almost exactly the same technique as the message bus was using? It is exactly the same technique as the message bus was using in the previous slide. So there really aren't that many. None of this is magic, by the way. OK, cool. So idempotency key is one way where you can say, look, I really don't want to process this payment to Ollie multiple times. I want to pay him. But I only want to pay him one time. I do like him, but you know. I only want to pay him one time. And so we remember often in those systems, oh yeah, well I've already completed that payment, so I don't process it again. Does it make sense? All right, idempotency key. The other idea is that sometimes, not always, but sometimes the processing itself can just be inherently idempotent. So if you're doing a pure write, so maybe the example is like I'm just setting some value to some number. Like if I set a value to 2 and I set it to 2 again, that's idempotent. Does it make sense? Like it has the same effect. A set, actually for both meanings of the word set, is pretty idempotent. So often processing isn't like this, but sometimes you get lucky and your processing is inherently idempotent and it's all good. Great. The option 3 is, I'm just going to quickly mention this and give you some reading material later. But the other option is something called conflict-free replicated data types. Martin Kleppmann, who gave a talk yesterday, introduced this idea there. He's done other talks that were also excellent that delve more into these ideas. But the general idea is that I want to be able to achieve agreement. In this case, I want to achieve agreement on the state between the sender and the receiver, or the producer and the consumer of the events, without explicitly coordinating between them. And so typically, I mean, this is very hand-wavy, but typically this involves some custom data structures and some custom processing. And there are lots of implementations of these things, but they're actually being actively worked on in research. So I would recommend not rolling your own. Common techniques, though, just to give you a little bit of intuition about how these things work. They're not magic. They're just smart people being very thorough. The typical techniques are like, remember what you saw, something like an idempotency key. Remember that I've processed this thing before. And then the other technique, which is a little bit subtle, is if something is deleted, you need to remember that you deleted it in case you get something else out of order. Does it make sense? So these two techniques, the idea of remembering what you saw and the tombstone idea of remembering that there was a deletion, between those two ideas, you're getting a lot of the techniques that are behind the CRDTs. Cool. Do not roll your own from first principles. This stuff seems so simple at the start, but please don't, because it's really hard. So there you go. All right, cool. Great. So that was event duplication. Now I want to talk about event ordering. So your problem is events are going to arrive out of order. You say why? I say because networks. Because networks. Network issues, I might get a delivery now, it's delayed, then I get the other, get a redelivery much later. Because processing time, if in the real system, I'm going to have multiple consumers in parallel, and one might be stuck or taking a long time processing, event number 1, and another instance of my consumer gets event number 2 before we're done processing event number 1. That's certainly a situation. And then also event redelivery is another example where later you might see an event that was produced earlier. Does it make sense, all these ideas? So this is a real problem. So, again, so the producer produced things in order because something was messed up in the network or in the print transport or something like that. We actually end up delivering things to the consumer in another order, and the consumer does need to process them correctly, let's assume. Yeah? So regardless of the order in which they arrive. So that's the problem statement. OK, cool. How are we going to do it? As with all things, we have multiple options with some trade-offs. So the first option is we sequence them and we reorder in the message bus. So again, this is kind of this buffering idea, very similar to what we were talking about a moment ago. So there's going to be a sequence number, very much like one of these idempotency keys. It's all one set of techniques. Sequence number that the producer adds. The message bus is just buffering up the messages. So it sees message 2, notices that it hasn't seen message 1, so it just waits. Yeah? Just waits to deliver, and then once it gets event 1, then it can safely deliver, say it's delivering them together, right? It's delivering event 1 and event 2, and then the consumer is really happy. Who's heard of TCP? That's this. That's this. All right. You could see, oh, sorry, my mistake. It's what I'm about to tell you. Okay, so option 2 is we do that same sequencing and reordering, but instead of in the transport, we do it in the consumer. So the transport delivers it to us out of order, and then the consumer reorders it. Sorry, this is how TCP works. Yeah? It's the consumer that is managing, requesting redelivery, reordering things silently, behind your back, and this is why that works. Has anybody heard of the TCP retransmission delay? That's a setting that if you're way low level, you have to deal with. Yeah. That's a setting that handles when the consumer might ask the sender to redeliver. All right, cool. So another totally legitimate technique. Great. And then yeah. And then, so that was about sequence. Those sets were about imposing an order, like imposing a total order on the events. Now another set of techniques is about not worrying about being comfortable with the idea that I'm going to receive events out of order, but just processing them in the correct order. Does it make sense? The first was about delivering an order, imposing an order on the delivery, and now I'm talking about having the processing be resilient to getting things out of order. Okay, so option 1 here is the simple case, which you hardly ever have, which is order-independent semantics. So let's imagine that I'm simply counting the number of events that I see. Like, it doesn't matter what order I get the events, they just come in that order, right? So that, if you have that, then that's great, very simple. You hardly ever have that case, though. Option 2, though, is something that at eBay we used to call notification and readback. So let's imagine that the consumer receives event 2 first. What the consumer is going to do is it's going to read back to the service. Well, so first, the event is just going to be a notification, right? The event's going to say, address changed. And the consumer is going to read back to the producer and say, oh, could you give me the current address? Does it make sense? That's the notification part. The event is just a notification, and it's the consumer's job, if the consumer cares about the data. Sometimes the consumer doesn't. In fact, often it's true. But if the consumer cares about the data that's current, the consumer will read back to the producer and get the current data, in which case, notice the states here, when the consumer reads back at the event 2 time, it notices that the state is 2. And when it reads back, even though it's received event 1 out of order, it reads back for the current state, and the state is still 2. Does it make sense what I'm saying? Yeah, cool. All right. Okay, option 3 is something called event sourcing. And there's lots of good thinking and talking about event sourcing, some of which has occurred at CraftConf. But here I want to just talk about how event sourcing can solve our problems of event ordering. So the general idea of event sourcing is that you store all the events in your log, and that log of events is your system of record, like an assets and debits in finance. So yeah, so you store all the events in a log, and then the great benefit of storing all the events in a log, even if you've stored them in the order that you received them, is that you can then reorder them when you're asked for them. Does it make sense? There are many other benefits of event sourcing, which we can talk about later if you'd like. But one really cool thing about event sourcing in this idea is that it almost naturally solves the problem of event ordering. I just write everything to the log in the order that I've received it, but then when I need to reprocess them, I can process them in the correct order and fine. Does it make sense? I'm just deferring the work and can do it when I know more. All right, cool. Well, great. So that was a very fast tour through microservices, through monoliths, and through event-driven systems. Köszönöm. I think we have a few moments for questions, which would be great. I'm also going to be around for the rest of the conference, so you can absolutely come up to me individually. I'd like to add this resource slide at the end because if you want to learn more, well, all right. It will be in the slide deck up on the thing. If you want to learn more about how to do Sagas, Katie McCaffrey's talk and Chris Richardson's talks, both of which are available on YouTube, you can just go and Google for them. And other things too. Martin Kleppman's book as well is really great. Okay, great. All right, cool. Questions, cool. Yes. If you split the DB, is there a method for data migration for large DBs? Yeah, data migration is a challenging problem. Wow, okay. It's really challenging. There are techniques about it. This is going to be the next talk for next year, as I'll add in the data migration section. The techniques are, you basically need to run the old system and the new system in parallel. So what you have to do is you have to start moving the new data over into the new system, and you backfill the new system, and you haven't like turned on the new system, but you're sort of slowly, you backfill the old data, and you're writing from into both old system and new system in parallel, and then after a while, when you're comfortable with the new system, you can turn it on. You have to leave the old system on for a while, and then once you're completely comfortable, you will never go back to the old system. You can migrate to the new system. Yeah, so there's no push-button way to do that as far as I'm aware, unless you're willing to take downtime. Like if you're willing to take downtime over a weekend, it's dangerous, but like that's a totally legitimate thing. I've never worked in a place where I could take downtime for the last 15 years, so yeah. All right, cool. Are there frameworks to not having to manually write the undo events in the Saga scenario? Yes, there are several. So that resources page that was up briefly, it's a reference to a talk by Chris Richardson, but he also is actively working on a framework. It's in Java, but that's cool, that actually implements Sagas. I think there are probably other people that are working on frameworks, but that's the one that I'm familiar with. If Randy falls somewhere between point A and point B, then only Perl can help him throw an event that travels back in time and resets his state to point A. Quaversal.
Okay, maybe one last question.
Okay, where does the UI fit in the service boundaries? Oh, that's great, yeah. You can, every time I say service, you can replace that word with application, and it still works correctly. So I hope that was enough to say that, but I'll just be more clear. There is nothing wrong and everything right with the idea that you could have UIs in those services, or more commonly, you have UI applications that use the services to get their job done, if that makes sense. So UIs in a microservice world are there. They're just usually not shown because the hard part is happening in the back. All right, thank you very much. Enjoy the rest of the conference. I'll see you around.